Welcome to the Deep Dive. Today we're getting into something really fascinating. Lightweight engineering materials. And more specifically, the cutting-edge ways we're figuring out how to actually machine them.
Yeah, it's a huge area. Think aerospace, space tech, automotive, even electronics. They all want these materials.
Right, for the strength-to-weight benefits, corrosion resistance, all that good stuff. They seem like the perfect solution on paper.
They are, but working with them is another story. Their properties, low density, sometimes not very stiff, or maybe they're reinforced with really abrasive stuff. They just don't play nice with traditional machining methods.
Okay, so it's not as simple as just swapping out steel for titanium on the production line.
Not at all. You really need different approaches.
And that's where we wanted to focus today. There's this innovator, ISCAR, and they've apparently developed some really specific tools and techniques. The promise is, better productivity, more precision, which is obviously critical.
Exactly. They're tackling those hurdles head on.
So, our mission for you listening is to dig into how ISCAR is managing this. We want to uncover some of the maybe surprising facts and insights behind overcoming these manufacturing challenges. Okay, let's unpack this then. We get why industries want lightweight stuff, but what actually makes them so tricky on the shop floor? What are the real headaches?
Well, it really varies quite a bit depending on the specific material. Take titanium. Great material, but it's very ductile, very tough.
Which sounds good, but for machining.
It means the chips it produces tend to kind of weld themselves onto the cutting tool. Sticky.
Oh, okay.
Yeah, so you get really rapid tool wear, and the surface finish on your part isn't great. It's a challenge.
A bit of a nightmare for keeping tools sharp, I bet. What about aluminum? We usually think of that as easier.
It often is, but aluminum has its own quirk. Very high thermal conductivity.
Meaning it pulls heat really well.
Exactly. But in machining, that means the heat generated from cutting gets pulled into the tool instead of being carried away with the chip.
Oh, I see. So the tool itself overheats.
Precisely. That heat softens the cutting edge. Tool life goes down, and workpiece quality can suffer too.
Yeah.
You might not hit the tolerances you need.
Okay, makes sense. And composites, like carbon fiber reinforced polymers and planes, they must be totally different.
Oh, completely. They're often very abrasive by nature, so they just chew through tools much faster than metals often do.
Yeah.
And because they're built up in layers, there's a big risk of delamination when you machine them.
Like the layers separating.
Yeah, like plywood peeling. It ruins the part's structural integrity.
Yeah.
Then you've got polymers, plastics basically. Low density, sure, but often not very stiff on their own.
So they add reinforcements?
Right, hard abrasive particles usually.
Right.
So you end up with this mix of something flexible but also abrasive, which is, well, surprisingly tough to machine accurately. Even things like metal matrix composites, MMCs, maybe aluminum with silicon carbide particles mixed in great thermal properties. But machining them means dealing with that hard particle, soft matrix combination. It's tricky.
Wow, okay. So it really is a unique puzzle for each material type. How has ISCAR actually engineered solutions for these very specific, diverse problems? It can't be a one-size-fits-all tool.
No, definitely not. ISCAR's approach seems to be looking at it from, well, multiple angles at once. The tool material itself, the actual shape or geometry of the tool, and then the coatings they put on it.
Okay, tell me more about the geometry part. How does shaping the tool differently help with something like titanium?
Well, for titanium, one example is their Quick X F-flute range. These use indexable inserts, little replaceable cutting tips, but with cutting edges designed in a very specific way.
How so?
The geometry is optimized to reduce the cutting forces needed and, crucially, to help get the chips out of the way cleanly. It helps control how the chip forms and breaks.
Ah, so managing those sticky chips we talked about.
Exactly. It aims for a smoother cutting action, less vibration, which is key for titanium. It's really about engineering that interaction at the micro level.
Clever. And you mentioned coatings. What do they do?
Coatings add another layer of defense for the tool. Things like titanium, aluminum nitride, or diamond-like carbon. These are super hard, slippery coatings.
So like armor for the tool edge.
Pretty much. They increase hardness, resist abrasion, and reduce friction. ISCAR has this Sumo Tech coating technology that's specifically mentioned for boosting tool life with high-temp alloys and those abrasive composites. It acts like a thermal barrier, too, protecting the tool from heat.
Got it. And for high-speed work, like with aluminum, where heat into the tool is the enemy.
Yeah, they have specific tools for that, too. High-performance milling cutters, things like their Heli-LU shell mills or multi-master tools. These have exchangeable carbide heads, which is quite neat, and also chatter-free end mills.
Chatter-free? That sounds important. What's chatter?
Chatter is basically uncontrolled vibration between the tool and the workpiece during cutting. It leaves a poor surface finish like ripples, and it's really hard on the tool, especially bad on thin-walled parts.
Right.
So these tools are designed specifically for high-speed milling of aluminum, aiming for great finish, long tool life, and minimal chatter.
Okay. And what about turning operations, like on a lathe?
Similar principles apply. They offer carbide inserts, again, the cutting tips, but with rake faces and chip breakers tailored for lightweight materials.
Rake face. That's the angle it cuts at.
Yeah, precisely. That angle influences how the chip curls away. And chip breakers are tiny features designed to literally break the chip into small, manageable pieces instead of long, stringy ones that can tangle or damage the part. Better chip control means less heat buildup, better life, better quality.
So it really sounds like the tool itself is just one piece. The way you use it matters just as much. What about the overall machining techniques ISCAR supports or recommends?
Absolutely. The technique is vital. ISCAR tools are often designed with high-speed machining, HSM, in mind.
So cutting faster?
Yes, but also often with lighter cuts. It can dramatically reduce cycle times, boosting productivity, while still maintaining precision and good surface quality if you have the right tools and machine.
Makes sense.
Another big one is minimum quantity lubrication, or MQL.
Less coolant.
Much less. Instead of flooding the part, MQL delivers a tiny, precise amount of lubricant, often in an airstream, directly to the cutting zone. ISCAR's tools are compatible with this.
And why is that better, especially for these materials?
It's really effective for materials like titanium that don't conduct heat well. Flooding might not even get the coolant where it's needed most. MQL is more targeted lubrication and cooling. Plus, there's a big environmental benefit. Way less coolant to handle and dispose of.
Right, that's a significant advantage. 2 birds, 1 stone.
Definitely. And then there's adaptive machining.
What does that involve?
It means using control systems that monitor the cutting conditions, forces, vibration, temperature in real time, and then automatically adjust the machine's parameters, like feed rate or spindle speed.
So the machine yaps on the fly.
Exactly. Using ISCAR tools with these strategies helps maintain consistent cutting conditions. This improves tool life, ensures you get high-quality finishes, even if you're machining really complex shapes or the material isn't perfectly uniform.
Okay, bringing this all together, where are these kinds of innovations having the biggest real-world impact right now?
Well, aerospace is a huge one. They're constantly pushing for lighter planes, for fuel efficiency, performance, sustainability. That means lots of aluminum, lots of titanium alloys.
And ISCAR solutions directly tackle the headaches of working with those.
Precisely. Tool wear, heat, surface quality, those are major concerns in aerospace manufacturing. These tools help address them directly, enabling lighter, stronger components.
And what about literally beyond our atmosphere, space applications?
Oh, absolutely. The space industry is booming, and the demands there are, well, astronomical. Extreme reliability, maximum strength, minimum weight.
Failure is definitely not an option there.
Not even close. So for satellites, rockets, exploration hardware, they rely heavily on advanced manufacturing for materials like titanium, high-strength aluminum alloys, advanced composites. The tolerances are incredibly tight.
I can imagine. Even tiny flaws could be catastrophic.
Exactly. And machining these high-performance materials naturally leads to faster tool wear.
Yeah.
So having durable, efficient cutting tools isn't just nice to have, it's absolutely essential for making space exploration possible and reliable.
Let's dive into one really specific, maybe cutting-edge example. You mentioned earlier how material science is even changing the tools themselves.
Yeah, this is really fascinating.
Okay.
Get this. Indexable shell mills, a type of milling cutter, but with the body made of titanium.
The tool body itself is titanium, not just the cutting edge.
Right. Traditionally, these bodies are made of steel, but steel is quite dense.
Okay.
And when you're doing long-reach machining, where the tool sticks out really far from the holder to reach deep into a part, that density, that weight, can cause stability problems, vibrations basically. Dynamic stability becomes critical.
So a heavier tool body is more prone to wobble when extended.
Exactly. So using titanium for the body is a fantastic solution. It's much less dense than steel, but still very strong. It dramatically improves that dynamic stability without compromising strength. Plus, you get titanium's corrosion resistance and anti-wear properties built into the tool body itself.
That's a really smart application of materials science. How do they even make a titanium tool body like that?
And here's the really cool part.
Yeah.
They use 3D printing, additive manufacturing.
Seriously, They 3D print the tool body.
Yep, and this isn't just a gimmick. 3D printing lets them create incredibly complex internal structures that you just couldn't make with traditional machining.
Like what kind of structures?
Sophisticated shapes for chip evacuation channels, they call them chip gullies, to guide chips away really efficiently. And internal weight reduction cavities, making it even lighter and more stable.
What?
And maybe most importantly, it allows for optimized internal coolant channels. They can design channels that deliver coolant precisely through the tool body right to the cutting edges. Super efficient cooling.
Pinpoint cooling right where you need it. That must make a huge difference to performance and finish.
A massive difference.
Yeah.
For best results, they often recommend mounting these titanium body cutters on special tool holders that also have anti-vibration mechanisms, like ISCAR's Whisper line adapters, to really maximize that stability benefit.
So 3D printing isn't just making the part, it's enabling a fundamentally better, smarter tool design.
Precisely. It's a perfect example of how manufacturing methods are evolving alongside material science.
This whole deep dive really highlights how comprehensive ISCAR's approach is. It's not just one thing. It's this integration of clever tool design, the right techniques, even how the tools themselves are made.
It really is. And that level of innovation is what lets manufacturers get superior results. Better productivity, yeah, lower costs maybe, but fundamentally it lets them meet the incredibly high standards needed in these critical industries. We're moving past just cutting metal into really precise, efficient material shaping.
So as you go about your day today, maybe think about this. These complex, often invisible advancements in manufacturing tools, in machining techniques, they're quietly enabling the future. Everything from how we travel in space to the cars we drive, designs that were once impossible are becoming reality. It makes you wonder, doesn't it? What will this kind of precision allow us to build next?